So I just erased the board, but put down the summary of what we did, please. So the average symbol energy, ES, is equal to EA times EH. EH is the energy of the pulse that we have used, which is this integral. And the new thing is this energy for the constellation energy, which by definition is the expected value of the amplitude squared. And amplitude is the random amplitude that we are transmitting with. And for independent equally likely bits, it's just the average amplitude squared. So if we have capital M amplitudes, we just square the amplitudes, add them together, and divide by the number of amplitudes. Okay. For a standard constellation, okay, so we will mainly be using what's known as equidistant M-Mary-Pam constellations. And these are constellations which are regularly spaced on the line, like this, and it's centered around the origin. So if M is equal to 2, we just put out 2 points here at some amplitude. Let's call it C, and C and negative C. Okay. So the distance between these 2 points is 2 times C. Okay. So this is for M equals 2. And then if we want to M equals 4, we simply add points to the left and to the right on the same individual distances. So it will be at 3C and negative 3C, like this. And then we just continue until at the end, in the general case here, we would need M, let's see, so I get this right, M minus 1 C here, and the leftmost point here will be symmetrically at minus M minus 1 C. And then all these adjacent points will be spaced by the same distance, 2C. Okay, so this is known as an equidistant constellation, where all the points are at the same distance around from each other. Adjacent points are at the same distance from each other, and it's centered around 0. And then for equally likely independent random bits here, we see since it's symmetrical here, we can just compute the energy for the right-hand side multiplied by 2, and then we get, it's the same in both directions. So it's 2 times 1 over M, sum from M equals, L equals 1 to M over 2. And then just take the right-hand side points here. And the first one will be at C, the second will at 3C, 5C, 7C, and so forth. So it will be 2C minus 1, 2L minus 1C. This would be the signal point. Right, for L equals 1, it will be C, L equals 2, it will be 3C, and so forth. And then we need to take this squared. And then we have the constellation energy. This. Okay, and I will spare you the details here. It's not very difficult. It's, you just expand this in, you look at your favorite table, or if you know these are geometric series. There are standard series for this. So at the end of the day, this will then become M squared minus 1 times C squared divided by 3. And it will be convenient to write this in the following form, as we will see later, that C squared is 3 times EA divided by m squared minus 1, like this. Okay, so this holds in general for any m-ary equidistant constellation. Okay, so, and of course this is for equally likely independent bits. Okay. Now, from our physics courses, we know that there is a relationship between energy, time, and power, right? So we know that power is energy divided by time, or rather, the energy we get over t seconds if we have the power p is the product. I mean, energy is p times t. Okay, so this one we remember from our physics courses. Okay. So now we have computed energies here, symbol energies. Can that somehow be related to the transmit power we need? Seems reasonable, all right? We have energy here, we have power here. We just need to figure out time here somehow. Okay. So during a long period of time, we transmit one pulse every capital T seconds, right? So in the PAM, we transmit one pulse, wait t seconds, transmit the second pulse, wait t seconds, transmit the third pulse, and so forth. So the transmit power is related to the symbol power when we divide the time between consecutive symbols. Okay, so let me write this different. It takes t seconds to transmit the symbol. Actually, it might take a little bit longer depending on the extent of the pulse, but nevertheless, over every t seconds we output a new symbol. Okay. So then the average transmit power then is P ES divided by T. Okay, so what is this T? Well, T is 1 over T is the symbol rate, RS. If you remember, how many symbols do we transmit per second? You're 1 over T. There was a question? No? Okay. So the average transmit power we need to invest in order to get a certain energy per symbol depends on how fast we are transmitting symbols. So we're transmitting symbols slowly, we get a lot of energy for the same transmit power. Okay, so this is symbol rate, and this is average symbol energy. I will very soon stop saying average because that's implied always when we say the symbol energy. Okay. So this works also for bits. So if we take EB, which is the average, again, stop using that very soon, energy per bit. We can compute that from the average energy per symbol. So how would you go from energy per symbol to energy per bit? Well, we know that one symbol carries a number of bits, right? How many bits is there per symbol? Log 2 of m, right? So if the total symbol energy is ES, and if we divide by the log 2 of m, we get the energy per bit. Or another way to write this is, of course, that ES is the log 2 of m times EB. So if we have a certain energy per bit, and we have log 2 m of those, that together forms one symbol. Okay. All right. So what is P now in terms of P is ES RS, right? Which is then, as we know here, EB times the log 2 of m times RS. But we also know that RS is the bit rate divided by log 2 of m. Okay, why do we know this? The symbol rate, each symbol carries multiple bits, so the bit rate must be larger than the symbol rate, right? So it's and it is the same factor log 2 of m here. So we see that we can cancel the log 2s of m's here, and we then get EB times RB, like this. Okay. And we see that there is a same transmit power can be written as in terms of symbols or in terms of bits. It's very symmetric equation, right? It's ES times RS or EB times RB. And this extends to anything, really, that if we output something with a certain rate, and we have an energy for that something, its energy times rate is power. Okay. But it has to be the same, right? It has to be symbols, or bits, or samples, or whatnot, right? Okay. So any questions on this? Okay. Now, it might seem a little bit disconnected now what we have been talking about, energies and powers and so forth, but bear with me now, because now we will show how this power and energy translates into error probability. Okay. But before doing that, there is actually one more thing we want to do here. So why is this? Okay. We then now need to move to the next lecture here. Okay. One more thing before we can compute the error probability, and that has to do with Gaussian random variables. This is also a review, so hopefully you know this material already, but there is some notation that needs to be fixed here. So if we say that x and then this wiggle, and then this curly n, and then mu sigma squared. What does this mean? It means that x is distributed according to something. And when it says n here, n stands for normal. So this is the normal distribution, or Gaussian distribution. And mu is the parameter, mu and sigma squared are the parameters of this distribution, and this is the mean or expected value, and sigma squared is the variance. So these are the definitions of this. Then the the PDF of this is the famous Gaussian bell shape, right? So, something like this. Okay, now it happens to be a zero mean because it's centered around zero. Okay, so if we have a Gaussian random variable that's distributed according to mu and sigma squared, we can write this. We have, and this is true for any distribution, if we take x and multiply with a and then add b, how is that going to affect the variance and the mean? Okay. It turns out that the scaling factor a here comes into scaling the variance, but squared. Okay. So multiplying with a squares the standard squares the variance, and it also multiplies the original expected value here. But the b thing only affects the mean. Okay. And we can then conclude the following very important thing that we will use soon, is that if x is a Gaussian random variable and we subtract off its mean and divide through by the standard deviation, we get a normalized Gaussian random variable which has 0 mean and variance 1. Okay. Note that there is no square here. So this is the standard deviation. Okay, not variance. That's a rookie mistake to do that. Okay, so it's not very difficult to show this. Maybe you've seen this before. Otherwise, it's not difficult. Okay, then we have the Q function. The Q function we use to denote the probability of the Gaussian tail. So Q of x is the probability that y is greater than x, where y is a standard Gaussian random variable. Okay, so you've seen this in tables before. So sometimes tables are actually taking the probability that y is less than some value x. Okay, so this is typically what you find in tables. However, in our course, we're more interested in the tail probability than the left-hand probability here. Okay, so Q of x is simply the integral from x to infinity. So it's the probability to end up in the tail here. And here's a very important relationship for our purposes now, is that if z is a Gaussian random variable with some mean and some variance, then if we're interested in computing the probability that z is greater than x, okay, can we use the Q function to do this? And yes, we can, by simply converting what's on the left-hand side here into a standard Gaussian random variable. That is a Gaussian random variable with 0 mean and variance 1. So we take z, and then we subtract off its mean and divide through by its standard deviation. Then we know that we have a standard Gaussian random variable here. And we have to do the same thing with the right-hand side of this inequality. So we take x, subtract off the mean of z, divide by standard deviation. And then by definition of the Q function, this probability is Q evaluated at what's on the right-hand side of the inequality. Okay, so this is just an easy way to compute the probabilities including Gaussian random variables. Any questions about this so far? You should have probably seen this in a probability course during your studies. If not, brush up on this a little bit. Okay, so we have now want to go back here, and what we want to do then is to say, okay, we want to follow the noise through the system to figure out how it can affect our probability of error. Okay. So what we do then is we model the noise here as a white Gaussian noise. And what does that mean? Well, it means that we have a random process, which is a sequence of random variables, where each random variable, if I sample n of t here, we get a Gaussian random variable. And if I sample n of t with 2 different time instances, these random variables are independent of each other. then we get white Gaussian noise. Another way to say that is that we have a zero mean Gaussian random process with an autocorrelation function that's of this form. Where here we have the Dirac delta function. Okay. This variable n naught over 2, why we divide by 2 here is of historical reasons. It's always been done, so there's no way back. So we will just have to have this 2 here. Okay. This constant is also known as power spectral density of this noise. Okay. This mysterious function, this delta function, you've seen delta functions before, I guess, right? So what are they? Very strange things. Very strange things. So if one wants to do the proper math here, it's complicated. But we can have a simple engineering interpretation of this, which serves our purposes here. So let's go with that. So instead of doing the complicated math, we just do a interpretation of this. So if we have a pulse here, a regular pulse, nothing strange with this. It's a rectangular pulse which has a width which is equal to epsilon. Okay, so we have here a width epsilon, and then it has a height here which is 1 over epsilon. And therefore the integral of this is equal to 1? Yeah, exactly. What's epsilon times 1 over epsilon is 1, right? And then for some reason we would like to make epsilon small. So we can make it smaller and smaller and smaller. And at some point we have a very, very thin pulse with very high amplitude whose integral is equal to 1. And that is what we call the delta pulse. Of course, this is mathematically not rigorous, but it's good enough. Okay. So we think of the delta pulse as something which is extremely small, extremely thin, extremely high pulse. And the nice thing about this is that it has this shifting property. So for all continuous functions f of x, if I take f of x, multiply with the delta function and integrate, then the output of that is just the function f evaluated for that x where the argument of the delta function is equal to 0. So it's sort of like a sampling function, if you like. You place the delta around the sampling point, x0 in this point, integrate, and out comes the sample of the function that you wanted to sample. Yeah, so you've seen this before, I hope. Okay. Now, let's go and look at the noise component here. Again, it's a little bit complicated to do this, so I will gloss over the details here. And some of the things I say now you have to trust me on. Right? So if we think of n as being white Gaussian noise with this power spectral density, then if I take the sample of n of t, I get a Gaussian random variable with 0 mean. But the problem is that the variance is extremely high. Actually, it's not bounded, so let's call it infinite. Okay, so here we have a noise sample which has 0 mean, which is somehow nice, but it has infinite energy, infinite variance. So it could take on extremely high values with high probability. So this is a bad noise, right? Bad noise. So it's non-physical model. There is no real signal that has infinite variance. But anyways, it's a quite useful model, I would say. Because it can be shown that if there is something that is like this, which doesn't exist, but if it would have existed, if we filter it, we get something which is well behaved. Okay, so we take the noise and we filter it through a filter with impulse response H. Then if we sample that, we get a Gaussian random variable with 0 mean and a finite variance. So white noise should never be touched. Okay, one should never work with white noise in itself. We should always filter it. And once we have filtered it, it is physical, it behaves as one would expect and so forth. So never ever be tempted to work with white noise in itself. Filter it first and then you work with it. Okay. So since our model here is that the noise, we can have any model of the noise if we like, but if this is a Gaussian noise, if this is the input to our receiver filter, then the noise component on the output of the filter is well behaved. Okay. And as a matter of fact, it will be, if we sample it, we get a noise sample, and that noise sample turns out to have 0 mean and this variance. Okay. And we see here that the variance, this variance is interesting. It depends on n0 over 2, which is noise property, right? The bigger n0 over 2 is, the more noise we have. Okay, so this is somehow the model of the noise. If it's high or low, we adjust this by this parameter. But it's given to us. But then EH here is the energy of the impulse response. So it's a design variable. But it turns out it doesn't matter what we put this to, we will get the same performance anyways. Okay. And I will explain that in a second. Okay. So the noise sample we have here is something which is 0 mean with a certain variance, and then we divide by EH, and then we get the noise sample here. And if we have a random variable and we divide by something, this will affect the variance of it, but not the mean. So the mean will be the same, but the variance would differ. It will become this instead. Okay, and why is this? It's because if the input variance is EH times n0 over 2, okay, so this is the variance before, and then we multiply with, then we divide by EH, then we need to multiply that input variance with this squared. This will be the variance at this point. Okay, so this is the variance here, and this is the variance here. And we can simply see that this is n0 over 2 times 1 over EH. Like this. Okay, according to what we did previously. Very good. So now we know how the noise goes through the receiver filter, what happens after sampling and the scaling. We get a noise sample here, which is a Gaussian random variable, 0 mean with a certain variance. And they are also independent for different cases. So any questions so far? Okay. So now we're ready to compute the error probability. Okay. So we will use pulse amplitude modulation with this equidistant constellation. And perhaps it's easier to say that we will transmit 3 bits per symbol. So we need 2 to the power 3, 8 signaling points. So let's drop the time index k here. So basically what we would like to do is to see how things progress through this chain, and let's drop k here just to have a little bit less to write. Then the input to the slicer z is the transmitted signal point plus this noise component n. And we know that this noise component is Gaussian with 0 mean and a certain variance sigma squared. And we saw that earlier that sigma squared is actually, has a variance n naught over 2 EH. Okay. So suppose we now have 8 pan, then we need 8 points. So we have 8 points here, equidistantly spread here. So the points is C, 3C, 5C, and 7C, and then symmetric. Then we have decision regions. The decision region boundaries is in this purple color here. It's in between adjacent signaling points. So the distance between a signaling point and its neighboring decision boundary is C. Right? So the error probability, if we transmit A equals A1 minus 7C, okay, we denote this by probability of error given that we transmit the first signaling point, PE1. So it's the probability that it's the probability that the received point does not end up in the decision region which is allocated to the signal alternative 1 here. Okay, so it's the probability that C is not in the decision region for A1. That is, we make an error if this is our transmitted point. Our receive point will be somewhere along this line. If it's to the left of this decision boundary, we will decode A1 and there will be no error. If it's to the right of the decision boundary, we'll make an error. And then we would like to compute the probability of this. Okay. So it's the probability that Z, which is equal to A1, which is, this is what we transmitted, plus noise, is greater than the decision boundary here, right? Then it will be to the right-hand side of this. Okay. And what is the decision boundary? Well, it's placed at negative 6C. Okay? And A1 here is actually minus 7C. So this is the probability that minus 7C, which is A1, plus the noise is greater than negative 6C. We wanted the probability that Z is greater than some value. Z is equal to A1 plus N. A1 is negative 7C. So we just write that. Probability that negative 7C plus N is greater than this. This we can write as the probability that N is greater than C. Okay. And then we do the following trick. We take N and then we subtract off its mean, which is 0, so we don't have to subtract. But then we divide by the standard deviation, which is sigma. And then that should be greater than C over sigma. And N divided by sigma is a standard Gaussian random variable with 0 mean and varies 1. And now we can use the Q function to evaluate this probability. Okay. So, to summarize, if we transmitted the first signaling point, this one, we make an error if the noise is such that it moves this point over the decision boundary into the adjacent decision region. And this is basically, this is equal to the probability that the noise is greater than the distance to the decision boundary. Right? And that happens to be very simple. Q function, C divided by sigma, which is, sigma is square root of N naught over 2EH. So the Q function of C over sigma is the Q of square root of C squared over sigma squared. Okay, now running out of space. Well, let's write it here. C squared and then N naught 2EH. Okay. All right. But what is the probability of error if we transmit 7C? Okay. We have not computed the probability if we transmit minus 7C. If we transmit this point, what is the probability of error then? When in doubt and things look symmetric, we just say, it's symmetric, it has to be the same. Okay. This is typically what you do, what I did during my studies in the exam, right? It looks like they're similar. Due to symmetry, it's the same. Actually, it is the same because the the noise is very symmetric, so it doesn't matter if it's greater than C or smaller than negative C, it will give the same result. Okay, so then we know the error probability here and here. Now, suppose we have one of these inner points. What is the probability of error then? So the probability of error, if we take, say, the second point here, we get an error if the noise is such that we move either to the right of the decision boundary or to the left of that decision boundary. Okay. So this is equal to the probability that the noise magnitude is greater than C. That either is to the right or to the left. Or stated in a different way, is the probability that n is less than C or the plus the probability that it's greater than C. Okay, and this we know is Q C divided by sigma, this one, and then this is the same here, so this is 2 times this. Okay, so now we know the error probability of all the points, and the total, the average error probability is the average of the conditional error probabilities. Okay. So for each ignorant point, we know what the error probability is. To get the average, we average over these points. All points are transmitted with the same probability. So the total error is the 1 over m sum from k equals 1 to m of this p, e, bar k. Okay, so this is the error probability we transmit the kth signaling point. And in our case, we had 1 over 8, and then we had 2 endpoints, which had a probability of error C, Q of C divided by sigma. Okay, so these are our 2 endpoints. And then we had m minus 2 inner points, actually 8 minus 2 inner points, 6 points, and all of them had twice the error probability of the endpoints. So something like this. Okay, so the 2 outer points and the 6 inner points. Okay, and if we add everything together, we get 6 times 2, that's 12, plus 2, that's 14. 14 divided by 8, that's 7 divided by 4. Q, C, sigma is going like this. So now we know the error probability of this constellation. Okay, so how does C and sigma, how does that relate to the noise and the transmit power? Okay, I will just go through that and then we'll break for the day. So C divided by sigma is equal to the square root of C squared over sigma squared. Okay. Now, way back, we related C to energy. Okay, it's not here on the slides, but let me just put this up. c squared, if you look at your notes, I have to look at mine too. Remember that's 3 times EA divided by m squared minus 1 in the general case. So we did this for equidistant PAM